Good morning here in Waldorf, and I hope the program is attractive enough to keep you here and not that you leave out for the golf course. But as most of you are young researchers, maybe that's not yet your sport. I'm very proud to present this first session to you today. I'm director of the Center of Computing Technologies at the University of Bremen and a computer scientist, and for me it's a great honor to chair this session with two really brilliant people of my field, and so I'm really excited to do that, and I'm really looking forward for the next two talks. As we look at the participants, we find a lot of female participants, which I think is marvelous, and in our field there are brilliant female scientists. However, if you look at our universities, at my universities, maybe at your universities, the higher you go up in the hierarchy, you lose sort of many of these bright people for whatever reasons. And we are all striving at our universities to get more women into computer science and mathematics. And I think it's very important to keep this intelligence in our field. And so for me, it's a very wonderful thing to have Barbara Liskov here today as a first speaker, because she's one of the 3 female Turing Award laureates. And I think there should be much more. And so for me, she's a hero in a way. And I think also for many young female scientists in the field, she is very important because she can show, yes, well, that's possible. And it's not a business only for men, but it's a business for everybody, computer science. Barbara Liskov is born in California. She did her bachelor at UC Berkeley, a wonderful place. I spent half a year there and I would love to go there again. But she studied mathematics and then went to Mitre Corporation and came back then to continue studying and met John McCarthy, well, one of the really great names, where she got into artificial intelligence, and she did her PhD on chess endgames. And she was one of the first women to do a PhD in computer science. She then went back to Mitre and she found out she's very good in programming and had a great interest in programming languages. She did her own operating system and programming system, Venus, and she developed a lot of concepts for data abstraction, for concurrent processing, for multi-threading and so on. And she is one of the pioneers in object-oriented programming, because many of the concepts she developed are now in all programming languages we use today, like Java or C++. Barbara got the Turing Award in 2008, and she got the John von Neumann Medal, and the Discovery magazine once named her one of the 50 most important women in science. And it's a great pleasure for me to welcome her here today. And even though she invented the Liskov substitution principle, there is no substitution for her. And so she's sharing her insights today on data abstraction, and I'm very happy to welcome Barbara here on stage today.
Yeah, well said. Thank you so much for that lovely introduction. So when I thought about the talk for today, I had to choose between talking about some of the current work I'm doing or to give you a talk that's really about the history of what I've done. And I decided to do the talk about the history because I think it's really interesting to the young researchers how ideas developed and where they came from. So when I got the Turing Award, and it was in 2009, this caused me to go back and think about the past. I really hadn't been thinking about those topics for quite a long time, and so it was very interesting to go back. I reread lots of papers. It was, and that's what I'm going to be talking about today. So I have a device here. Yes. The problems that I was looking at that led to the development of the idea of data abstraction had to do with the complexity and size of software. So software is really complicated. The systems we build today are gigantic, millions of lines of code. And they do very complicated things, sometimes things that people's lives depend on, but even when it isn't your life, they're doing very, very complicated things. And to make things worse, they might be concurrent, they might be distributed, so we have very complicated underlying things to deal with. And how to master the complexity of software has been, ever since I started working in the field for sure, and even continues today, to be one of the topics that computer scientists have to look at. And in fact, several of the talks you've heard during the symposium have been touching on that issue. So what have we done to address complexity? Well, one thing that's changed, oops, sorry, that's not what I meant to do. How do I get rid of that? Oh, it's not up there, good, okay. Except that, yeah, okay, let's try that, yes. So one of the things that people have done, and the field has changed tremendously since when I started working in it, is they have figured out all sorts of ways to do things. So when I started off, if you wanted to do sorting, it wasn't exactly clear how you should do it. And people were developing interesting techniques for sorting. Today, if you want to sort something, you go and you look in a textbook and you see there's this technique and this technique and this technique, and you choose one of them. Or you go to your libraries and you just pull something out of the library and use it. And this is true for data structures, for algorithms, and also there are very many interesting protocols at this point that it's just part of what we have available to us, and we don't have to think so much about it. Not to say that we've invented everything, but we have a lot more to stand on. However, this is really only a small part of complexity, because when you develop a software system, you have this at your disposal, but these are just tools, and you have to figure out, how do I organize the entire program? And I'm going to take advantage of this, but the organization is an even harder problem. And the question of addressing that sort of complexity is the topic that people working in programming methodology have been trying to address. And I'm going to talk about programming methodology as it was then. So this is when I started working in this field. And programming methodology has a way of spilling over into programming languages sometimes, and I'll talk a little bit about programming languages. So what I'm going to do in this talk today is I'm going to talk about programming methodology as it developed, starting when I started to work on it, and some of what happened in programming languages. So I started working in this field in 1970. I was working at MITRE at the time. And as the introducer told you, I got my PhD at Stanford, working in AI. Halfway through my PhD, I realized that I wasn't interested in AI. Or rather, that's not the right statement. I felt AI was too hard. And I maybe felt that the software systems field was better for me. I decided to stick with AI to get my thesis done, because after all, the point of being a graduate student is to get your thesis done and go on and do stuff. But I planned to switch as soon as I left graduate school. I wasn't able, at the end of graduate school, I had no offers for a good position at a faculty in a university in the US. This was different from my male colleagues. They got offers. And at the time I thought, well, it's because I'm not good enough. You know, they're better than me. But in reality, what it was is the old boys network at work. And so what would happen is some professor at one school would talk to a professor at another school. They'd say, I have a great young man for you. And that's how people were getting jobs. At any rate, there I was. And I did have an offer from MITRE, where I had worked before I went to graduate school. And then I was a programmer, now I was coming back as a researcher, and MITRE was good for me because my husband lived in Boston and I needed to move back to the Boston area. It also turned out to be really fortuitous that I went to MITRE rather than a university because I was making a huge change in field. And at a university I would have had to spend a lot of time teaching. Here I was able to focus entirely on research. So I worked at MITRE and I started off working in computer architecture. Then I developed a small time-sharing system called Venus. And then about 1970, I was asked to look into the software crisis. There I am, the software crisis. And what happens at MITRE is it works mostly on projects for the government, the US government, and they put out requests for proposals, and MITRE bids on some of these. And the government was very concerned about what was called the software crisis. And what this meant, and by the way, this continued, it continues to this day, but it was much more evident in the 60s, 70s, and 80s. People would try to develop software systems. They would spend millions of dollars, they'd spend hundreds of man-years, apologies to Fred Brooks, and at the end the system would fail, and you'd see an article in the newspaper about this catastrophe and that catastrophe and so forth. So this was a big concern to the government because they were developing complex systems. And by the way, partly the problem was exacerbated by the fact that you could see the cost of hardware. Machines were very expensive. People didn't understand the cost of software. It sort of didn't appear on the balance sheet. And so they had a tendency to make the problem even worse by buying less hardware than they needed and expecting that the software would be able to make up the difference. Okay, so that was the software crisis. And as I said, programming methodology is the field that developed to look into how this should happen. And programming methodology actually looks at two distinct things. One of them is the design process itself. How do you, starting with a problem, figure out a structure of the program that's going to solve this problem? The second one is, what is the structure of these programs that you're looking for? And I'm going to talk about both of these today. Now, what I did when I started working in this field, which was a field I really knew nothing about, is I did what you always do when you move into a new field. I read the literature. And at that time, there wasn't as much in the literature. So it was a little easier to look at all the literature. And I did what I could. I read as much as I could. And I'm going to talk, I went back and read these when I got the Turing Award. These are great papers, and I'm going to talk about a few of them. I recommend that if you hadn't read them, you should read them. I think in computer science, we don't pay enough attention to what has happened in the past, and it's really important, especially for those of you who are researchers, to keep track of this. So the first paper I want to talk about is this famous paper by Edgar Dijkstra, Go-To Statement Considered Harmful. It may not occur to you, those of you in computer science or those of you who've done any programming, that there was ever an issue with the go-to statement. The programming languages that we use today don't have go-to statements in them. But at the time, they did. And Dijkstra wrote this, actually just a letter to the editor of the Communications, a very controversial piece at the time, explaining why go-tos were a bad idea. And what he said in this paper, and the thing that's really sort of striking about it, because people didn't respect software at the time, that's still a problem to some extent. He said, programming is a difficult intellectual activity. It requires a lot of brain power to write programs. And one of the reasons why it's hard is because a program is a static representation of a dynamic object. So what you have to study is just a linear representation of what's going to be going on. But what happens when the program runs is you have a dynamic execution. And his point was that if you can keep the dynamic structure of the program close to the static structure, it'll be much easier to understand what your program is doing. And I think a good way of thinking about this is actually debugging. When you find an error in your program at a particular point in the execution, you need to figure out, how did I get to that point? And if you can do this by just looking at the linear structure of your program, it's a lot easier to figure this out than if the program is jumping all over the place and you don't know how you got there. And with go-to statements, people's code can jump all around. People used to talk about this as a bowl of spaghetti. So this was a very controversial paper at the time. And there were a couple of reasons for this. One was Dijkstra didn't always say things as nicely as he could have, so he had a tendency to get a reaction. People were insulted, you know, and the truth is you can write a good program no matter how lousy your program language is. You can write a good program in assembly language, but people don't always do that. And you can write a bad program in a good programming language. So the language is only a tool. You can use it or misuse it. But the other thing is people had legitimate worries about whether it would be sufficiently expressive to use a language without go-tos, because you're taking some power away when you remove them from the language. And at that time, the control structures that were available were not quite as powerful as they are today, and so this was also a legitimate concern. For example, in the absence of an exception mechanism, passing a label as a parameter is a way of getting the exception to go to a different place than the normal return, and that was something people sometimes used. So that was the paper by Dijkstra. Here's another paper, a very excellent paper. Nicholas Wiert was a professor at Stanford when I was there, so I got to know him. He was probably an important reason why I thought I would go into systems. Anyway, this is a paper about program design. So Nicholas was trying to think about a very systematic way of developing programs. And his idea was, it's a top-down process. Now, we know today that design is not entirely a top-down process. You have to, as you get lower down in the design, you may discover there was something wrong with your reasoning. You may have to back up and backtrack and try again. But design has to be fundamentally top-down, because if you don't keep an eye on what it is you're trying to develop, how can you possibly end up with a structure that accomplishes what you're trying to do? What Nicholas Wiert had in mind here was a very orderly process, and what he said was, well, you start with the problem you're solving, you make one design decision, you then write an abstract program, which he thought of as being a sequence of comments. You convince yourself that that abstract program, if it existed, would have solved your problem, and then you select another design decision and continue the process. And the example he used was the 8 queens problem. And he said, we're going to solve this problem row-wise. So we're going to, at any stage, have a solution that works for the first n rows. And then we're going to try and add the n plus first row. And the 8 queens problem says the queens can't attack each other in any way. So the question is, can I add in the n plus first word a queen that won't attack all the existing queens? If yes, I'll go forward. If no, I'll back up. And he showed how to do this in an orderly process. So this is a very nice way that people can approach the design problem. The final paper I want to talk about is this paper by Dave Parnas. Parnas did wonderful work in program methodology. And at this particular year, 1971, he published 2 papers about modular decomposition. What was striking about this paper and reading it after the fact today is Parnas says, programs are composed of modules, but I don't know what modules are. And this was, in fact, the state of the art at the time. We knew we had to break programs into pieces, but we didn't know what these pieces were. What he said was, whatever they are, we have to actually get a handle on the connections between modules. In other words, what one module can expect from another module, how they interact globally. And then he came up with this definition that said, the connections between modules are the assumptions which the modules make about each other. So he's saying it's not just the arguments that are coming in and the answers that are going out, it's all the other ways in which they interact with one another. Okay, so I read many other papers, but these are the 3 I thought I would talk to you about. Okay, so Parnas is bringing up the issue of modularity, and I want to stop and talk about modularity from a modern perspective, and then I'll get back down to where I am. So Parnas says a program is a collection of modules. Okay, why is this a powerful idea? Well, what's powerful about this is that if you can describe the interface of the module by what we today call a specification, then you have a way of decomposing the program into pieces that you can work on independently. So we've already heard Leslie was talking yesterday about specifications. He talked about both sort of high-level specifications, input-output specifications, and also lower-level ones about how the module implementation was really working. I expect that Tony will talk about specifications. I've always been most interested in interface specifications, the sort of pre and post conditions of calling the module. So if each module has an interface that's described by a specification, then we have a way of decomposing. The implementation can be judged to be correct or not correct, depending on whether it meets the specification. And if you have a using module that uses this other module, you can reason about the correctness of the using module using the specification of the module it's using and not paying any attention to how that module is implemented. And this is a huge simplification because when a module is implemented, it might make use of all sorts of other modules. And so there's a huge amount of code you don't have to pay attention to. And I just want to point out for you in the audience, especially the mathematicians, how much this is like proving theorems. Modules are like lemmas. You have a statement of the lemma. You use it in proving the correctness of a higher level lemma or the theorem. And you don't worry about the details of the proof of the lemma when you're proving something at a higher level. And at each stage you work on this single problem using the statements of the lemmas and theorems as the basis of what you're doing. So I came from mathematics, I think math was just deeply embedded, and so these kinds of ideas, when I'm thinking about programming math, it's a great preparation for computer science. Okay, so here's an example of a module, and this, was Leslie's talk yesterday. A sort routine is a module, and the specification says what he said yesterday. At the end, the elements of A are sorted, and they're a permutation of what they were when you started. And you don't worry then about whether it's quick sort or bubble sort or whatever is going on. Okay, so that's a modern understanding of modularity. And as I said, it has huge benefits. I've been talking about local reasoning. That's a very important benefit, probably the most important one. But you also have the benefit of modifiability. If you don't like the way your sort routine is implemented, you can re-implement it. And the using modules will be unaffected by the fact that you have a different implementation now because they only depended on the specification, not on the details of the code. Or if you have an error, you can correct it and it won't affect the using modules. So that's a second very important benefit. A third benefit is independent development. You can hand out different modules to different people. They all know the specifications, so they can be working independently. And I think independent development was the main reason, or a very important reason, why people were using modularity at the time I started this work. However, in the absence of an understanding of what modules were, and furthermore, a lack of understanding about what specifications should say, it wasn't working all that well. And a further problem was that they only understood about procedures as modules, and they weren't nearly powerful enough to allow you to develop the kinds of systems we wanted. For example, a file system is a module, but it's certainly not a procedure. They weren't even used very much. I had the experience of maintaining a huge program in assembler, and it was mostly just sort of straight line code. It went on and on and on and on. There was occasional call of a procedure, but there was no modularity for the thing as a whole. And the connections were very complicated. And partly, this was, so this is the time of Algo 60 and its successors. Algo 60 had a great idea and a bad idea. The great idea was there was block structure. And that means that code in an inner block has data that's protected from code on the outer block, so you get a kind of modularity that way. The bad idea is block structure, because at the outer level you have global variables and everybody can use them. And in the days when I'm talking about, that was how programs were structured. There was a lot of global data. All programs were free to interact through this global data. And so the connections were very complicated. Okay, so I read all these papers, a bunch of others, and I'm thinking about methodology, which I found extremely interesting. It's clearly a very important problem. And I realized that I had invented a methodology when I was working on the Venus machine, which was the first work I did at MITRE, a little time-sharing system. And what had happened in Venus is that I had a small team of programmers. We were doing quite an ambitious project, and I was very worried about how we were going to get the job done in a short period of time. And so I developed a rule. I said, we're not going to have global variables. We're going to partition the state. And we'll have modules, each module has a piece of the state, and the other modules aren't allowed to access that state. Instead, each module will provide a set of operations. I think I have a picture on the next slide. I wrote this up and described it for a paper in 1972, but here's a picture of what I was doing. I partitioned this system. Each piece of the system, each partition had some state, and the rest of the world didn't access that state, but it could call operations, and there were multiple operations associated with each partition. And Venus was organized using this idea, and I think it kept us out of a lot of trouble. So I was thinking about this, and I realized this was a methodology nobody had been talking about, although clearly akin to things that people were talking about. And so I wrote up a paper and put it into the FJCC. In those days, there used to be these big computer conferences where everybody in computer science would go. The field's gotten a bit bigger since then. Okay, so now it's 1972, and at this point I moved to MIT. And what happened was, I had written up a paper on Venus. As I told you, in 1968, when I got my PhD, nobody was interested in me. By 1971, when my paper was in SOSP, which is the top systems conference, and it was a prize paper, the Title IX had been passed, which said that women have to have equal opportunity at universities getting funding from the federal government. So MIT was one of those institutions. I don't think all institutions were paying much attention to this, but MIT actually was paying attention. Jerry Wiesner was the president, and he decided this was important. He pushed down on all the departments, and so my department, at that time electrical engineering, later electrical engineering and computer science, was taking this seriously. And when I gave my talk at SOSP, my program chair was Jerry Salzer, who was a professor at MIT, and Corby, Professor Corbateau, who was another Turing Award winner, was at the meeting. And they approached me and asked me to apply to MIT. So I did, and they offered me a job, and I moved to MIT in the summer of 1972. And this was really a good time for me to move, because I had made the switch into systems, and not only that, but I had found a problem I was passionate about, and I wouldn't have been happy at MITRE than being asked to switch topics to another thing. I was ready to be a professor. You know, there's a good and bad piece to being a professor, just like there's a good and bad piece for block structure. The good piece is you get to do what you want. The bad piece is you get to do what you want. And that means you have to find money for it, you have to actually have the ideas, you have to, be self-confident enough to push it through and so forth. Okay, so here I am in 1972, and there's this problem that's just consuming me. And it's the question of, these are great ideas in programming methodology, but nobody understands how to use them. And I felt this was true for my paper, it was true for everybody's paper. You would read them, you would say, very compelling, this is exactly how you ought to solve the problem, that they would use as a little example. Then you would be confronted with the problem you were working on, and you'd say, well, what do I do here? How do those ideas apply to my problem? And I think the problem was these papers were very informal, and they had vague notions of what to do, and we needed something much more defined so that we could sort of hang on to it. And at some point, in either the fall of 1972 or early in the winter of 1973, I had one of those wonderful aha moments that sometimes you're lucky enough to have, where I suddenly saw that partitions could be connected to data types. So in retrospect, this seems obvious. Okay, so here's a partition. Okay, it's got some hidden state. It's got a bunch of operations. Well, it's an object, right? The object has state and has a bunch of operations. But at the time, nobody saw this connection, although when you read the papers after the fact, you can kind of see it sort of floating around in there. But it was very important to make the jump, because data types are something programmers understand. They were already using languages with data types. These data types were abstract in the sense that the hardware didn't support them. It's just that there was a very limited number of them. And so what I was saying is, well, let's just do more of the same. You don't have a set in your language, invent one. it'll have a set of operations and so on. So I could see this was going to be important because it got us into the programming language domain, and I believe programmers think in terms of programming languages, and so what you can get into the programming language is going to really influence what they're able to do. Another point is that this is an abstraction, and actually when you design, you think of abstractions. You're trying to think of what's this thing which, if it existed, would be very useful to me in building my program. And so far we had only had procedures. Now we have something more powerful, an abstraction from data. Okay, so I had this great idea, but it was, a vague idea. And so the next thing I did was I worked on, how to sort of firm it up. And I started working with Steve Zillis, who was actually a student at MIT, but an employee of IBM. And he had a similar idea. And between us, we had a very broad perspective on programming languages at the time, because, of course, for my thesis in AI, I had used Lisp. And so I was very familiar with that style of programming. Steve worked for IBM, which was the major player in programming languages at the time. That's where Fortran and PL1 and so forth were coming from. And of course, we were reading the literature as well. We knew all about ALGOL and ALGOL-like languages and stuff like that. And of course, we read the literature because we were moving into the programming language domain. That's what we were actually doing. And I'm going to talk about a couple of papers. Here's the first one. This paper by Ole Johan Dahl and Tony Hoare about hierarchical program structures. This is actually a paper about Simula 67. And Steve and I looked carefully at Simula 67 because it has classes in it. It has subclasses. It does not have encapsulation, which is a very important property, and I'll get to that more in a minute. And we decided ultimately the notion of subclasses was going to be a distraction from what we were doing. We were interested in the class idea, but not the subclass idea. And so we sort of put it aside. This paper, by the way, was published in what we refer to as the Little Black Book. And this Little Black Book, which was very influential, had 3 papers in it. There was another paper by Tony about data representations, which was also very influential. And there was a paper by Dijkstra on design. And this was a book everybody was reading at that time, especially people working in programming methodology. Okay, the other paper I want to talk about is a very important paper by Jim Morris. Jim has been for many years a professor at CMU. This was called Protection in Programming Language. And Jim was talking about what is it that makes modularity work in this paper. And so he said, here are 2 rules you have to follow if you're going to get the benefits of modularity. The first one is that the module has private data, and code on the outside had better not modify that data. And this is critical for independent reasoning, because if the code outside can modify your data, then you don't have any local control, and so you can't reason about correctness locally. So that's sort of this is half of the encapsulation principle. But Jim said, oh, and also, by the way, the code outside shouldn't even read the data. And that second thing is less obvious, but has to do with the ability to do modifiability. Because if the code outside can look at the data, then if you need to change the implementation and have a different representation, you're not able to do it. In some sense, you've taken the representation and pushed it into the specification, so you have a much more complicated specification and a lot less freedom in what you want to do. So he said those are the 2 rules, and that is what encapsulation is. Stuff on the inside is totally private, and all the code on the outside can't even look at it. And then Jim went on to say, well, how could we support this in a programming language? And he proposed what was basically encryption. He said, we're going to seal objects when they go out, so think about we encrypt them, and then when they come back in, we use our own secret key to decrypt them, and nobody will be able to see them, and if they've modified them, we'll notice when we decrypt. Of course, nobody would ever use a system based on encryption because it'd be too expensive. So he had the right rules, but not a mechanism that was going to work. And what Steve and I were looking for was a practical mechanism, and we were in particular interested in whether type checking could do this. And we decided, yes, this was going to work, and so we wrote a paper in the summer of 1973 that essentially gave you the notion of a language containing abstract data types. This was a huge, very impactful paper. A funny thing about this paper is that we wrote it over the summer of 1973, and my memory of the summer of 1973 was that it was sunny every day in Cambridge, Massachusetts, which of course is not true. But Steve and I used to work separately, meet for lunch every day, and there was a lovely courtyard, and we would meet outside in the courtyard as often as we could. And I think this is an interesting story because it tells you about the unreliability of memory. And memory really is not all that reliable. This is a small thing, but I find my memory about many things is not that reliable. And this is, by the way, why history is so difficult, a completely different topic. Okay, so that paper proposed a programming language where people could define new data abstractions with a set of operations and a set of objects where they were totally encapsulated, and the operations would be the only way to use the objects, and the whole thing was going to work through type checking. And we also talked about a sketch of the programming language. So now we're in the fall of 1973, so I'm at my second year at MIT. I've gotten over the startup tangent where I was asked to teach a course that electrical engineering without any electrical engineering background. Another funny story along the way. And 3 students showed up in my office, this is my recollection again, asking to work with me on this project of going from abstract data types to an actual programming language that supports it. And here's their names, Russ Atkinson, Craig Shafford, and Alan Schneider. And they, along with me, were the principal developers and designers of this programming language CLUE. I talked to Russ a while ago, and he informed me that he did not show up in my office asking to work on CLUE. Instead, he was my advisee, and I said to him, why don't you come and work with me? I've got this interesting project going on. Okay, so I'm not a person who ever took pictures of my group, and I didn't try very hard, but I don't really have pictures of as we were at the time. But this is one picture from about that time. That's me, and this is Jack Dennis, a very important figure in machine architecture. And Jack was very helpful to me at MIT, and actually, he was never a collaborator on any of this, but he was an interested participant in listening to what I had to say. Now, I felt that in this talk I did not have time to talk about CLUE in any detail, and plus, of course, we have a lot of people here who are not computer scientists, and so I would quickly get sort of beyond what I think you can follow. I'm going to talk a little bit about CLUE, so I'm going to just do a tiny amount. And here are some facts about CLUE, just to get started, and these were kind of what we decided going in. First of all, CLUE has static type checking, which means that you declare your types, the compiler does complete checking at compile time. It often finds program errors this way. I actually think static type checking is very important for building programs that really work. In a way, this was my reaction to Lisp. I wrote my program in Lisp. It doesn't have static typing. It would be so annoying after spending some hours trying to figure out what a bug was to discover that if we'd only had static type checking, I would never have encountered this bug. And so I had a strong desire for static type checking. On the other hand, Lisp was heap-based, and it had separate compilation. Also, 2 things that were not common at that time. There was a lot of discussion at that time about how really you want to use the stack, and objects are not such a good idea, and the heap was really sort of, people viewed that with great suspicion, whereas Lisp is entirely heap-based with a garbage collector, and I felt that was an important way to go. Today, of course, it's, everybody's like this. And it turned out that that was an important decision for the development of CLUE, because one of the nice things about putting your object in the heap is it doesn't matter how big they are. And so you can develop your implementation later or change your implementation, and the rest of the code isn't going to be affected by this. And then separate compilation, that's another thing we have today, but it wasn't that common at the time. And in Lisp, of course, it's just the way you do things. So I was very influenced by Lisp in both positive and negative ways. And then the other thing is there were a bunch of stuff I ruled out. As I mentioned, I ruled out inheritance because I felt that would be a distraction. I think, what's going on, I ruled out gotos because I absolutely believe Dijkstra's arguments. And I ruled out concurrency as a distraction. And this is how you have to do things when you're doing research. If you're trying to work on an intellectually difficult problem, you try to throw out whatever you can so that you can focus on the main point and not get distracted on other things. I think Jack Dennis was disappointed when I threw out concurrency, but thank heavens. I mean, we still don't know how to manage programs with concurrency. That would have been a major distraction. Okay, so CLUE had a bunch of mechanisms. One of the odd things about CLUE was it was way ahead of its time. And in some sense, the programming language community has still not caught up. And I'm just going to show you a little bit about it. So clusters were the things we had that are like classes that we used to implement abstract data types. Polymorphism is the idea that when you write a program, it doesn't work for just one type, it works for many types. And polymorphism becomes much more compelling as soon as you have data abstraction, because now instead of just a set of 5 types that the programming language supports, you have a very large, growing, changing number of types. And it's clear that you don't want to only sort arrays of integers. You want to be able to sort any array of things that are sortable, or maybe any array-like collection of things that are sortable. So you would like to build one sort routine rather than having to implement it over and over again. Or it's clear that you don't want to define only a set of integers. You would like to define a set of arbitrary type. So that's the problem we were struggling with in CLUE. I'm going to tell you about polymorphism, iterators, and exception handlers. So here's the polymorphism issue. I would like to define a set of T, where T is some arbitrary type. And what I'm showing you on the slide is the syntax for CLUE. I'm defining a cluster, that's our class. It's parameterized by some type T. It has a set of operations that the users use to interact with set objects. And inside, hidden from the user, is how we chose to represent sets and the implementations of all the operations on sets in terms of that implementation. Now the problem with polymorphism is, for many polymorphic things, not every type works as a parameter. Even for sets this is true, because T has to have an equality relation, so you can tell whether a particular object, when you try to insert it, is in the set already or not. And it's even more true if I was talking about sorted sets, then I'd need a less than, or if I'm talking about sorting, and so on. And we wanted to be able to handle this polymorphism problem at compile time. And it took us a long time to think of how to do that. It was probably 1975 before we figured out a solution. And this was our solution. We added a where clause to the header of the module. And this one says T has to have an equal operation, which is a procedure that takes 2 T's and returns a Boolean. Notice that this is entirely syntactic. It has no semantics. So I didn't capture the idea that it's got to be an equality relation. I captured the type information. Types are actually a small piece of the semantics of the type. So the operations and the syntax captures an important part, but not the whole thing. You need a specification as well. Okay, so that was our solution. And then once you have this, you can do separate compilation, because when I compile the set module, I can depend on T having my equal operation that I need. And when I use it, the compiler can check to make sure that T really does have that equal operation. So this gave us the ability to have generics with separate compilation. CLUE also has iterators, and the thing about abstract data types is that many of them are collections. You often collect things into a set, a hash table, a blah, 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 whatever it is. And when you collect things into a collection, that's usually because you want to do something with the collection, like I'd like to print it, or I'd like to add it, or something like that. And to do that, you need an iteration construct. And so we came to realize that we needed an iteration construct. It wasn't strictly necessary, because we could have fudged it in the code. We could have, for example, removed each element from the set one after another and then printed them. But sometimes you want to use the collection for a second purpose, so that's not really a very good solution. Or we could have complicated the abstraction by, for example, turning it into an indexed set so that we had the ability to iterate over it. That's even worse, because you really want your abstractions to be as simple as possible to do the job, and you don't want a programming language mechanism that forces people to complicate things. Well, I took my team of students to CMU, where Bill Wolf and Mary Shore were working on Alphard. This was probably the summer of '75, but I don't remember exactly. And they told us about something called generators, which are like the iterators in, they're like what goes on in Java today. And we listened to this and we said, oh yeah, this is going to be a great solution for writing iterations, except that it's kind of an ugly idea. And on the plane coming back, my student Russ Atkinson invented iterators, which are like procedures, except that they yield things multiple times. So you start off a loop by calling, in this particular case, the members operation of the set. This is an iterator, and it produces the first element, and you run the loop body, and when the loop body's over, you return to the iterator, and it does it again, and when it's done everything, it returns, and that's the end of the loop. So that's a very simple idea. It's a kind of 90% solution. There are some iterations that can't be handled this way, like testing same fringe over 2 trees. But, you know, we're engineers, and it seems better to have a solution that can be used 90% of the time and is simple and straightforward, and then when people need something more complicated, they can always implement their own generators. Okay, we also had exception handling, and I see I'm getting close to the end here, and this is because I'm a great believer in strong specifications, not only ones that say what they should say, but also ones that where the module will handle every legal input. So everything that's type allowed as an input ought to be handled by the module, but you can't always do the same thing in every case. All right, so I'm at the end of Clue. At that point, I had to figure out what to do, and I actually jumped into distributed computing. I had a choice of language design or something new. I didn't have any great ideas at that point, nothing along the lines of data abstraction, so I decided that wasn't the right path to follow. Distributed computing was a dream of Bob Kahn's, and I'm sure Vint could tell you much more about where this dream was coming from. But I read a paper of Bob's in which he said, wouldn't it be great if we have distributed programs that run on many computers connected by a network? Nobody knew how to build them, so I thought, great research problem, and I jumped into distributed computing. And I did lots of work. I mostly worked in distributed computing from then on. I also continued working on program methodology, and I guess I don't have time to tell you about the Liskov substitution principle because we have used 40 minutes, right? Yes, okay. Except I do want to tell you that I never invented the name Liskov substitution principle. What happened was I explained what it was, and that was in 1986, and then sometime in the 90s I got a letter saying, or an email saying, can you tell me if this is a correct interpretation of the Liskov substitution principle? And that's when I discovered that people were talking about it, they'd given it a name, and so on. All right. So I'm basically at the end now, and what I discovered when I got my Turing Award was a very interesting fact. I discovered that modularity based on abstraction is the way things are done. And I honestly had not realized this because I had been thinking about distributed computing. I wasn't paying much attention to what was happening in the sort of wider world of commercial programs and so forth. My husband was online every day looking at the commentary. And one day, and as you know on the internet, not all comments are nice, but one of the things that he encountered was a comment that said, what did she get that award for? Everyone knows this anyway. And this, you know, was clearly not intended as a nice remark, but actually it's a huge compliment. Because what it meant was that this idea that I had invented, and you know, others thought about it at the same time, had become so ingrained that everybody did know it. Now, I chose not to talk about what I'm doing today. I just want to mention I've gone back to programming language design to some extent, and I've been working on multi-core computers and how to make programs with conflicts work well. Just to show you that, you know, you sort of go on, and I switched to yet a new field, multi-core programming, after working in distributed computing for a long time. I don't believe, this is the end of my talk, that I believe that the young researchers are the ones who define the future, and I'm not very, I don't believe I have the vision to tell you where you should be going. So I feel more comfortable sort of telling you what I do, and then I pass the baton to you, and I'm interested in knowing where you think we should go next. Okay, so thank you very much.
Thank you. Thank you, Barbara. We are a bit behind time, but we just eat up a bit of the coffee break because commuting and the introduction took a bit longer. We have time for a few questions. Here's the first one.
So thank you very much for the very nice talk. So it's a little bit of pity that I was not talking more to you before at this event. So really great talk. So if you look at today's programming languages, so the major programming languages, so is there something like a language construct or a concept that you would say this is clearly missing today?
I think the really big problem, I think there's lots of small improvements you can make to programming languages. I think the really big problem is we still don't know how to build parallel programs. And if somebody had a great idea about how to make it easier to implement concurrent programs, I'm not talking about embarrassing parallelism where you can just say, you know, do all this stuff in parallel and then maybe you have a barrier at the end. I'm talking about programs that actually have conflicts, need to work correctly, we need to handle their race conditions, we need to figure out how to do the right kind of synchronization. If we could come up with some idea about how to do that, that would be a major step forward.
Yes.
I actually have a follow-up question about that. So you talked during your talk about how you thought that not dealing with concurrency at the beginning was helpful because it was so complicated.
Yeah.
If you would have included it at that time, do you think writing parallel programs may be easier now because it would have been more ingrained?
No. I think it would just have, I would just have gotten down a rat hole. I will say that I do think the most important thing for proper concurrency is modularization and encapsulation. You really need to have mechanisms and obey those mechanisms where the code that's implementing the abstract object that has a lot of concurrency inside it is totally in charge of the synchronization, and code on the outside is not able to interfere with that. But I think you need more than this. You need support for transactions. I think you need, I just don't know. As I said, I think this is really an important problem, and it's come to the forefront with multi-core computers. So I hope that now people are starting to think about, what's a new way of doing things.
Leslie Lampert.
I'm afraid I have to point out one error in your last slide, which said everybody is doing it. I thought that too, and I wrote a little piece for Wired, and I discovered it was, well, not true. And there's a part of the world out there that does something called agile programming, which essentially ignores everything that was learned in the 70s.
Yes.
And I hope the people, the young people here will be able to try to correct the error that's being propagated now.
Yeah, did somebody say people are clever monkeys? Sometimes an idea comes up in the professional community and everybody kind of jumps on it. It's partly the theoreticians want to make it precise. People are playing around with it. Ideas in programming that violate encapsulation and abstraction are really bad ideas. And one thing to keep in mind, a couple of things. You often develop a first version of your system, and then the system grows way beyond what you expected. And so you really have to be thinking from the beginning about good principles for program design, even though for a small program you can get by with a lot. The other thing is if you're building a large program in a team, the success of your project depends on the weakest member of the team. So it really is good to have very good hygiene when you build programs that everybody obeys so that everybody can follow the rules. And another thing to remember is that reading code is much more important than writing it because it's read many times by you, by others, and so forth. And so again, good hygiene that makes it easier to understand the code after the fact is really important. So I absolutely agree with you. The statement was not mine, I read it off the internet. But absolutely, you see these trends coming up and you think, oh, for heaven's sakes, why are they doing this? and it becomes wildly popular for a while. I think it always dies out, but still.
Should we go for one more question? It's your coffee break afterwards, but.
To what extent have developments in hardware encouraged or gone along with the developments in programming techniques? For instance, when I started, we had 256 words of random access memory, and now you have gigabytes. That means you don't have to use go-to statements in order to reuse every scrap of code. The large size of memories makes it possible to have memory abstractions that require copying. You've got space to copy things. To what extent does the development of hardware, for example, stack managing opcodes, to what extent have these things helped you develop your concepts of programming?
I would say that the biggest problem with hardware these days is actually the games they play with shared memory semantics, and even with not the semantics of executing instructions, but the fact that they will execute instructions out of order. And people writing code, especially at the low level, need to be aware of this and sometimes put in extra instructions in their code in order to make sure that things are happening in the order that they need to happen in. I have to say sometimes the languages are not doing such a good job either. The compilers, like the C++ compiler, is busily reorganizing your program, and you have to be aware of what it's doing in order to make sure. And I'm thinking mainly about concurrency here, because sometimes it really matters that at this particular moment all the processes are synchronized or something like that. Otherwise, I guess I don't worry too much about the hardware, although debugging is much harder than it used to be, because when the program is not being executed sequentially in the way that you expect, it can be much more complicated to figure out what's going on. So in a way, I think hardware has been going in a direction that's not that helpful to software, because it makes the problem harder. But on the other hand, of course, we all want machines that perform well. So I think we just have to learn how to live with this, and we also have to decide what is the right memory model for parallel machines. Yeah.
Let's thank again Barbara Liskov for this talk.